So you all survived the prom and all that good stuff, so
Allegedly.
you all look very nice for the ones that I saw. I was down there. Okay, so let's chit chat about work, okay? So, it was prom, you all probably might have offloaded a lot of the information that you learned. So, there's two criteria when you talk about work. One version is that you have to exert a force, and the other thing is that it has to move in the direction of the force. So, if I just hold up this block, I'm not doing any work because it's not moving in that direction. But if I lift it up, I do work. If I lower it, if I do work. If I push it, I do work, okay? So there's your two criteria. Now, you can have motion without any work being done. So like if this was the magic frictionless block, and I gave it a push, I would do work to make it move. But if this was the magic frictionless block, I wouldn't do any work to keep it moving because I wouldn't have to exert a force in that direction. So you can have motion without work being done, okay? As long as it's a constant velocity and as long as you're not exerting a force in that direction. Now, when you lift things up, so this is what we talked about on Friday. So let's say I've got this block. So one option is that I just lift it straight up, okay? So I take whatever the weight of the block is, multiply it by that height, boom. Work is going to equal the force times that height. Now, if you have a ramp, oh, okay. So the advantage of the ramp is that you increase the length, but you decrease the force. But as long as it's frictionless, that's a whole key, then the work's going to be the same. If I make the ramp even longer, I'm still going to do the same amount of work. I'm just going to exert less force over a longer distance. Now, don't throw time into this, okay? Time is when you're going to talk about power. So, like for example, when you get to number 8, okay? So on number 8, this is when you're going to take this bucket of dirt and you're going to lift it up, okay? So you've got to lift two things. You've got to lift the bucket and you've got to lift the dirt. So to find the mass of the dirt, you're going to take the density, which I gave you, multiply that by the volume, there's your mass. Multiply that by G, there's the weight of the dirt, add those two numbers together. So, your answer to number 8 should be like 10 to the 5th joules, okay? Pretty big number. And then to get your power, that's just work divided by time. So it's like the rate at which you do work, okay? So the faster you do work, the less time there is, the more power that's required. On number 9, with your dragging the block, so here's the block, you're walking along like this, okay, and you're dragging it. So make sure you have that visual right. So I've given you the horizontal force. So that 462 newtons is the horizontal force. That's in the direction of motion. So the first thing you want to find is the tension. Well, if you look, that's the hypotenuse, right? So your answer to your tension has to be bigger than 462 newtons because it's the hypotenuse. So you know this angle, you know the side adjacent to it, maybe throw in a little cosine action, find the tension in the rope. Now, but on part C, where it asks you how much work is done in dragging it, only use the force that's in the direction of motion, okay? This isn't like an inclined plane problem. You're not dragging it up this angle. You're just dragging it like this. So when you're doing that work in moving it, just use the 462, multiply that by the length. Now, on number 12, and this is this visual that we did with Kara on Friday. So in this case, you have like two different objects, mass A and mass B, okay? So the whole key to this is that you have to keep track, is it the same force over the same time, or is it the same force acting over the same distance, okay? Because remember, force times time equals change in momentum. Force times distance equals work, okay? They're kind of related, but they're very, very distant cousins, okay? They do share the force part of it. So what I'm looking for, like on number 12, A, where it says which one's going to travel further. Okay, well, the easiest thing to do is start with the idea that force equals mass times acceleration. Oh, okay, right? So obviously, if the force is the same, the one with the smaller mass is going to have the larger acceleration. Now, that in and of itself is not a justification. So what you could say is, oh, okay, right? Since the time is going to be the same, and the distance traveled is going to be 1/2 AT squared plus V naught time. So here's what I'm looking for, like on 12A. You would say, okay, one of these is going to have the larger acceleration. And the one with the larger acceleration, because the time is the same, so the one with the larger acceleration will travel the greater distance. So this is what I'm talking about as far as like giving an equation to justify your answer. Okay, so you can say, okay, one of them, whichever one you think is going to have the larger acceleration, is going to travel further because it's going to have a larger acceleration, it's going to be the same time, that's going to travel a greater distance. Okay, so that's the kind of thing I'm looking for on that one. On number 10, with President Biden going up the escalator, that answer should be something times 10 to the 4th. And here's how, there's two ways you can work number 10. You can either take the force parallel and multiply that by the length, or take his weight and multiply it by the vertical distance that he's going to get lifted up. Okay, those are your two options. You do the same math, you just change the sequence when you do the math. Okay, but what you can't do is take his weight and multiply that by the length of the escalator, because that force isn't exerted over that length. It's only his force parallel that's exerted over that length. Okay? All right. Anything else you want me to go over on that assignment? Going once, going twice, so okay. Hand out yonder lecture notes. Okay, so here's the next big unit, which is going to take us about a week and a half, 2 weeks to get through in various forms, and that's going to be energy. So here's the anomaly about energy, is that everybody knows what energy is. Okay, like when you all walk in the door, Matt, can you do me a favor? Thank you. So when you all walk in the door, I can get an idea of how much energy that you have. Okay, so like when Elise walked in the room this morning, it's like I could just tell. It's like, oh, it's Monday morning after prom. She doesn't have very much energy. Okay, Matt usually walks in. He's kind of usually happy. Hey, Mr. Rookie, how's things going? Okay, and I can, when you all walk in, I can get a feel for just how much energy that you have. And the same thing with me. It's like, hey, what's work camp like? Yeah, it was pretty laid back, a little bit wound up, got his cup, he had his caffeine this morning. Okay, hey, life is good. So when you look at energy, here's the simplest definition. Is that if energy is capacity to do work. Okay, so this is why you study work before you study energy. So energy is the capacity to do work. So let's just say it's Sunday morning, it was yesterday morning, 24 hours ago, okay? It's 8 o'clock on Sunday morning. And your mom comes into your room, you've been at prom, you've been at after prom, you probably been asleep maybe for a couple hours, okay? And your mom comes in your room and says, hey, you know, here's the story. Aunt Martha is coming over. The house is a disaster. I need your help to clean the house. I mean, you say, Mom, I just don't have the energy. So from a physics perspective, what you're saying to your mom is that you do not have the capacity to do work. You do not have the capacity to take that vacuum cleaner, hold it in your hand, push it across the floor, and do work. Because you would be doing work. You would be or pushing the broom, the mop, whatever it is, okay? You would be doing work. You would be exerting a force over a distance. You look at your battery in your car, okay? You've ever had a dead battery in your car? Or your phone battery goes dead, okay? When that happens, you have lost that capacity to do work, okay? So the simplest definition of energy is that it's the capacity to do work. So if you look at energy, there's two broad classifications of energy, okay? You have kinetic energy, and that comes from the Greek word kinesis, which means motion, okay? And then you also have potential energy, okay, which is stored energy, okay? And no matter what, they're all measured in joules. So joules and energy is this great unifying theme across physics, across chemistry, across biology. So you all exist and you all have energy because on a cellular level, your body has the capacity to take the energy that is stored in the food, which indirectly comes from the sun, okay? Without the sun, this whole energy process stops. So the sun provides energy, it turns it into grass, cows eat grass, they make milk, it makes grain, you have cereal, you have coffee, you have donut, whatever that is, okay? And so you're just taking that energy and you're just changing forms of it. So when you look at this whole idea of like, we talked about the conservation of momentum, and we said, oh, hey, momentum is a conserved value. So whatever momentum you have at the beginning is the same thing as what's going to happen at the end. So the same thing is true of energy, but this is like on a universal idea. So if you look at subscribe to the Big Bang Theory, so all of the energy and mass that ever existed in this universe was contained in that singularity. And then something happened, and that energy and time began to exist, space began to exist. Nothing existed before the Big Bang. And so that's a whole long discussion about hyperinflation and what happened and all this good stuff. So all the energy and mass that was ever destined to exist in this universe was existing in that one small singularity. And then something happened, the universe then came into existence. And that was roughly about 14 billion years ago, give or take about 10 minutes, roughly, something like that. So when you talk about kinetic energy, there's two broad types of kinetic energy. You have what we call translational, and that's 1/2 mv squared. Okay, so like if I take yonder tennis ball, okay, and I throw this to Matt. Matt, you ready? Okay, so I'm going to throw that to Matt. So I did work. I exerted a force through a distance, and I created kinetic energy. Now, Matt changed the kinetic energy because he caught the ball and he slowed it down. So Matt, give us a throw back. Okay, so kinetic energy is the energy of motion. So let's talk about whether it's a vector quantity or a scalar quantity. So if we define this direction as being positive, I could say, okay, that's going to be 1/2. Let's say the tennis ball has a mass of 1/2 kilogram, and let's say that it's moving at 6 meters per second squared, okay? So I got 36 times 0.1, which is 3.6, half of that. I got 1.8 joules. Now, here's the deal. If you look at this units of kilograms times meters squared over seconds squared. Well, yesterday we said work was Newton meters. Well, Newton meters is kilograms meters per second squared times meters, which still gets you kilograms meters squared over seconds squared. Okay, so it's all the same thing. Now, Matt throws it back to me. Matt throws it back to me at negative 6 meters per second. Okay, so Matt throws it to me with the opposite direction, right? Same speed. Is that still going to have the exact same kinetic energy coming back to me as I threw it to Matt? Yeah, even though it's negative 6 meters per second, guess what? It's still going to have the exact same amount of kinetic energy. Mainly because that velocity is squared. So even if you have negative velocity, you still end up with the same kinetic energy. So based upon that, do you think energy is a vector quantity or a scalar quantity? Karen? Yeah.
Scalar.
Because now, momentum is different. If you talk about momentum, because momentum is mass times velocity. So I would have a positive momentum throwing it towards Matt, but when Matt threw it back to me, it would have a negative momentum. Okay? So momentum can be positive or negative. So that makes momentum a vector quantity. Kinetic energy is just a number, so that's just it's just a scalar quantity because we don't give it a direction. All right. Now, the other type of kinetic energy you can have is rotation. So if I take this wheel, right, and give it a spin, so Kr, and this is all on your equation sheet, is I butt squared. So, Miss Pfeiffer, what's the I going to stand for?
Inertia.
Moment of inertia, right? Omega is what?
Velocity.
Yeah, how fast you're spinning. So if you look at these two equations, they both have a half in them, right? This is mass, a measure of inertia. This is moment of inertia, how easy it is to speed up or slow something down. This is how fast you're moving. This is how fast you're spinning. Okay, so you're multiplying the same quantities together. And oddly enough, this gets you joules as well. Because this is moment of inertia, if you remember, is kilograms meters squared. Okay, omega is radians per second. We don't worry about the radians, so that's squared. So we still get kilograms meters squared over second squared, which is still going to be joules. So I'm at rest, boom, I now have rotational kinetic energy. I stop it, I don't have any. Okay, so there you go. Same idea. And again, no matter which direction I spin it, because it's omega squared, that's still going to be the same quantity. Okay. Now, potential energy. So potential energy can take on the most forms. So if you look at, actually, especially your generation, what drives your social interactions, what drives so much of what happens in your life, is potential energy stored, what we call UI. Okay, so potential, any type of potential energy is shown by the letter U. Okay, and then the subscript tells you what type of energy that is. So this is electrical potential energy. So one of the coolest things we've done as a society is figuring out how to store electrical potential energy. Because without that capacity, okay, we could have cell phones, right? You could have laptops, you'd have whatever. But if we didn't have the capacity to store electrical potential energy, then the only way it could work is if it was plugged into a wall. Okay, that's it. So it's like, oh, talk about a strobe. It's like, oh, we got to get the work cancer. We got to get seats closest to the outlets, because that's the only way it could work. If you've ever seen the footage of the old first generation of cars, okay, at that time we didn't have batteries. We didn't have the capacity to store energy in a battery. So what you do to start your car is that you would go out and you had a crank. and you would insert that into the front of the car, and that would latch onto the engine. And you'd sit there and you'd turn that crank, and that's how you would start your car. So you're still using potential energy, but it was potential energy stored in your body that then you would turn into mechanical energy when you would turn the crank of your car. So imagine it's like, oh man, I gotta go start my car. All right, pull out the crank, boom, give it a swirl, boom, okay, now we're off. So without batteries, imagine how your life would be different. So if you look at what I think is going to challenge different generations, okay? So let me give you a quick history lesson. So my father was born in 1927 and died in 1996. So Dad grew up on a farm out by what is now Cheney Lake, okay? Just on the east side of the dam. And when he would come into town, and this would have been early 1930s, whatever, okay? Number one, 21st Street was a set of wagon ruts, okay? That's it. It was just a set of wagon ruts. So they'd have to hook up the team of horses to the wagon. They'd leave early in the morning. They'd come into town. They'd get whatever that they needed, turn around, and go back. And so coming into town was literally a day-long trip, okay? By the time you got the horses hooked up, took the time, drove all the way into town, got whatever supplies that you needed, and then turned around and went back. So going into town took an entire day. Now it takes you, 15 minutes to drive that same distance. So, so by the time when my dad was born, and by the time Dad passed away, he saw flight, okay? Flight became, airplanes became, very commonplace. He saw the invention of the jet engines. He saw transcontinental flights become common. He saw Neil Armstrong walk on the moon, saw the space shuttle. So my father's generation saw a huge change in how we move, okay? From hooking up a horse-drawn wagon up to seeing a man walk on the moon, okay? So that was a huge change. My generation has seen a huge change in communication. So I remember in 4th grade, I grew up at Cheney, Kansas. Went through grade school out there. And first off, this is what we call this is the time what we call BC, which stands for before cell phones. Okay, there was a time before cell phones, shocking as that may be. And your phones existed like on the wall. Okay, there was no like battery powered phones. The phone was on the wall, and we had like the old rotary dial phone where you put your finger in, and there was like, if you've ever seen that, it's like a round wheel like this, and had holes in it. Like if you wanted to dial the number 9, you put your finger in the number 9, and you'd roll that around, and then you let go of it, and it would go, and it would come back. So that's how you dial the numbers. And you had 2 different types of phone lines at that time. You had a private line, or if you wanted that, you would pay the extra money to get a private line. Or you had what was called a party line. So if you were on a party line, like your household would share that same phone with like 3 or 4 other households. So what you'd have to do is that you'd have to pick up the phone and listen for the dial tone. So if you picked up the phone and somebody else was already on the line, you would hear that conversation. So you'd pick it up, theoretically, politely, realize that they were talking, and then you just put that back down. And so imagine you as teenagers having like a party line where, number one, you'd have to be right there in the house. That's the only time you could talk. And then you'd run the risk of having that conversation listened to by 3 or 4 other neighbors. It's like, oh my God, you talk about no privacy whatsoever. Oh my God. So in 4th grade, a friend of mine, Mike Denny, he got a touch tone or a push button phone. Okay, it was cool. After school, we all ran to his house to go look at the push button phone. It was the coolest thing because it was the first phone that we'd seen that wasn't like a rotary dial. And so like, oh my God, this is the coolest thing. Like, look, you don't have to dial. Okay, he had the first. Anybody know the first big video game? It's called Pong. okay? And so, and he had that game, so it was cool because it was like ping pong. And you had a dial, and you would like move these bars up and down on the screen, and a ball would hit and it would bounce, and your goal was to like move this thing so it would hit, and then that ball would bounce, okay? And that's how you would play ping pong. That's why it was called pong. Like when I did my junior research paper in high school, you had to go to the library, and there was no internet, there was nothing like that. Like you would actually have to get books off the shelf. Or if you wanted an article out of a magazine, you would actually have to go get the magazine, you hope they had it, and then you would write down that information. There was no copy, paste, anything like that. And then when you had to submit it, you actually had to like type it on a typewriter and then pull that out. And so now, I've got my phone and I can say, ask my phone anything like, hey Siri, what's the high temperature going to be today? And that information automatically comes up. And so my generation, from the time that I was born up to now, has seen a huge change in how you access information, how you communicate that information. Got a buddy of mine in Brisbane, Australia. Hey, Tim, how's it going today? Great, And that communication is instantaneous. So now you have the capacity to talk basically anywhere around the world, and you have more information at your fingertips than any other generation has ever had. So what I think will challenge your generation, oddly enough, is energy. So more so than any other time in the history of the world, we've become dependent upon energy. So like, if you remember last fall, it was on a Friday, and we lost electricity to parts of the building, okay? We had to shut down school because like I couldn't teach in here. It isn't like I have windows that I can open and I can let natural sunlight in, okay? We had to shut down school. Look at the price of gasoline. Okay, hey, it's pretty cheap, right? Because when you buy gasoline, fundamentally you are buying potential energy. When you plug your phone in at night, you are storing potential energy, okay, that you can then use to run your phone, okay, to run your car, okay, hey, your battery has a car in it, okay, you're storing potential energy. So, but unfortunately, energy comes with a cost associated with that. And so now the concern is that, okay, to generate all that electrical potential energy, we've been burning coal for a long time, okay? So here's the short version on how coal plants work, is that you go in and you mine the coal, which is also very energy intensive because of the machinery involved. You put it on a train, you ship it across the United States to wherever that plant is, and then you burn the coal and you heat up water, and we'll go through all those calculations. The amount of energy involved to heat up water is incredible. And then that energy of the water turns into steam. You heat up the steam even more. And then that steam has a tremendous amount of kinetic energy. You take that steam, it hits a turbine, the turbine spins, we generate electricity, and then we ship it from like Jeffries Energy Center up by Manhattan. We ship it all the way down here to Mays, Kansas. I turn on the lights, or I plug in my toaster and I can make toast. Okay, and so that's how every energy story ends, that, oh, we can make toast, okay? And that's fairly inefficient. So, but we've got to have it, okay? So we as a society basically are, what you generation especially has to decide, is that how we want to continue to produce electricity? And so hopefully, if you look at a shift in terms of how energy is done, and so this is the beauty of like the solar panels that are out here. So we get energy from the sun, carrying little bundles of energy called photons. It strikes the solar panel. It generates electricity by exciting the electrons. We take that energy and we ship it, 100 yards, and we can make toast. And so, but that's been a huge transformation in terms of how that's going to play out. You have wind turbines, you have solar panels that you didn't have before, mainly because it wasn't cost effective. Like I wouldn't have done the solar project 5 years ago. It was too expensive because you would not have gotten a return on the investment. But now solar panels have become so cheap that now it's actually cheaper to produce electricity that way than it is from a coal power plant. And then you get into battery storage. Like, okay, because that's always the knock on wind energy or solar energy or something like that, because it's like, well, that's great when the sun is shining or when the wind is blowing, but what do you do at night when the sun goes down? And again, battery storage, the ability to store UI wasn't cost effective. But now, like the cost of energy to store in batteries is dropping like a rock. So with that said, now that cost to store energy in batteries, especially even like grids, what they call grid-sized batteries, is dropping like a rock. And so what you're going to see, hopefully, in your lifetime is a shift from a central location where energy is being generated out to more and it was like a spider web. So you have one big plant and that energy would flow out like a spider web. So now what you're going to see, hopefully in your generation, is that whether it's wind, whether it's solar, whether it's even like the next generation of nuclear power plants, where you generate electricity in a more local area, and then instead of like one spider web going out like that, now you have like a tapestry of different energy sources where that energy can flow in different directions. So we're still going to need the energy. What your generation is going to have to decide is that where do we get that energy? Okay, so stand up, take a stretch. I know you all have been sitting, and then we'll continue this discussion. All right, so let's talk about potential energy. So we talked about UI, right? Energy stored in a battery, energy stored even in like chemical bonds. So like when you go to the gas station and you buy gasoline, you are fundamentally buying potential energy, okay? And because that energy is stored in the bonds, and then your engine has the capacity to take that potential energy stored in the chemical bond and turn that into mechanical energy. Now, the reason that you can't fill up your car with water, it's like, oh, well, let's burn water. We have a lot of water. Well, the problem is that water doesn't have very much potential energy in terms of being able to burn it. So if you think of like a roller coaster, okay, so you have this energy up here stored in gasoline, okay, and then your car engine has the capacity to take that energy stored in those bonds and have it go downhill, and then you end up with two byproducts of the combustion process, if you remember your chemistry. You get carbon dioxide and water vapor. So those are the two main things that come out of a combustion process. And so that's the knock on gasoline-powered engines, is that yes, they work well, we've had them for years, but every time you drive your car, you have the emissions of carbon dioxide. So everybody says, oh, let's have battery-powered cars, which sounds good, okay, and it does. Like I drove that Ford Mustang was out here. I test drove it. It's an amazing car. But then the knock on that is, well, if you're burning coal to generate electricity to store energy in the car, why don't you just burn the gasoline in the car? And that, because that's how we've always generated electricity. But now if you can sit there and go, well, if we can generate that electricity using wind turbines, solar, nuclear, whatever, and you don't have any carbon dioxide produced in the energy to run your car, then it becomes a carbon neutral situation, because you're not even producing carbon dioxide in the production of the electricity. Okay, so we got UI. So we're going to talk today about UG, and that's gravitational potential energy, and that's going to be MGH. So here I've got this block of wood. So let's say we're going to take this block, I want to lift it up. So let's say that it has a mass of 1 kilogram. You all know what G is, and let's say I lift it up to a height of 1 meter. So if you look at the units, you get kilograms, meters per second squared, times meters. Oddly enough, you get kilograms meters squared over second squared, which is also a measure of joules. So you can also have us, okay, and this will be later on, we'll talk about us. And that's energy stored in a spring. So like here I've got this little ET thing, right? So I'm going to wind it up, and there's a little spring in there, okay? Now, when I wind it up, am I doing work? Yes, because I'm exerting a force through a distance, right? So I do work. So the work that I'm doing is I'm storing energy in the spring. So now when I let go of that, okay, the energy that I store as potential energy is changing into kinetic energy. Now, some of that energy is going into sound because you can hear it. Some of that energy is going into friction, okay, because there's friction between ET and the blocks, okay? So, all of that we're doing is changing forms. And so this is the beauty of the idea of conservation of energy. So if you look at all the energy that existed in the universe, it was pure energy. And it began to cool down. And as it cooled down, it changed into mass. And so even if you look at what I just did, that energy in the spring is 1/2 kx squared. Don't worry about this equation. We're going to spend a lot more time talking about it. This is called the spring constant, and this is how far you compress or stretch the spring. But so Einstein equated all of this with his equation, E equals mc squared. So this is mass, this is the speed of light squared. And again, you're going to get the same units. You get kilograms, meters squared over seconds squared. Okay, it's the exact same thing. So Einstein couldn't say E equals mc. Because if he just took mass and multiplied it by the speed of light, which is just a velocity, he would have momentum. So to make the units work out, it had to be E equals mc squared. That's the only way you can get kilograms, meters squared over seconds squared. So if you look at all the energy that existed, which is now existing as us, which is now allowing me to have a sun, which is producing energy, which allowed me to have breakfast this morning, which now I have energy in my body, which I can use to wind up the spring to make ET have potential energy, and then ET changes that into kinetic energy. All it is one big energy transformation. So, even if you look at like a pendulum, so let me spin this over here. Okay. So, I got this pendulum, right? And I'm going to lift it up. Now, when I lift it up, am I doing work? Yes, I exerted a force through a distance. Now, at this point, I have a certain amount of potential energy. So what you'll see is that Mother Nature doesn't like potential energy. Mother Nature much prefers kinetic energy. So at some point, Mother Nature and potential energy got crossways. Some social medium, they posted a picture, made a comment, Twitter, Instagram, Snapchat, whatever. They don't like each other. Okay? I don't know how it got started, but they've never liked each other. So when I store that potential energy, as soon as I let go of it, it's going to start to change into kinetic energy. And the path doesn't make any difference. If I lift this thing straight up, like say to the height of my chin, I store a certain amount of potential energy, and that's going to change into kinetic energy as it falls. If I lift it up to the same height right here, I store the exact same amount of potential energy. And when it hits the bottom, it's still going to have the same amount of kinetic energy. Whether I just drop it and let it fall, or if I hold it up like this, the path doesn't make any difference. Potential energy changes into kinetic energy. Now, because energy has to be conserved, I'm going to hold this up against my nose like this, okay? I let go of it. And I knew that there was no way that was going to hit my nose on the way back up. Why? Why did I know I didn't have to worry about it hitting my nose? What'd you say?
It lost some.
I didn't hear what you said there.
It lost some.
Yeah, it lost some energy, right? It was moving through the air. We lost some of that energy in the form of heat. So thermal energy is the great dissipator of heat. So when I do this, okay, right like this, let go of it, okay, and even if I wasn't losing any energy at all, I gave it 2 joules of energy. So as it fell, I still have, at any point, 2 joules of energy. At the bottom, it has 2 joules of kinetic energy. Back back up over here, it's going to have 2 joules of potential energy again. Now, obviously, if I let this go over a period of time, what's going to happen?
Stop.
It's going to stop. Now, that energy still exists in the room. So this is kind of a cool idea. Is that I've been teaching in this room since 1996, okay? And there's been a lot of energy that's happened in this room. A lot of laughter, a lot of thermal energy, a lot of noise, okay? Labs, all this stuff has been going on. So from an energy conservation perspective, all that energy still exists in this room. It's just changed form. So when you all come back for your 10, 20-year reunion, you can walk into this room and go, you know, I contributed to the energy that existed in Bergkamp's room. It's changed forms, but it's still there. And so like, somebody got really, really bored, and they determined like, even like when you talk or laugh or make noise, that's energy. So they did the movie, was Monsters, Inc., where they harvest the energy of like screams or laughter, okay? So someone did the math, like if you could yell, ah, like that for like 8 hours, and you could harvest that energy, that would allow you to make a pot of coffee, okay? So if you could yell and then take that energy, that would allow you to have enough energy to make a pot of coffee. Problem is how do you harness that energy? So if you look at like prom, for example, on Saturday night, you had all this energy, you had all this noise, you had all these people moving around, right? And you had a tremendous amount of energy. So if we could find a way to harvest that vastly diverse energy and refocus it back into making electricity, oh, okay, hey, there's part of our energy crisis. But the problem is that energy gets so dispersed and so spread out over a period of time, it's hard to get that energy back and refocused. Okay, so these are going to be the 2 types we're going to deal with, us and up. Now, here's how work becomes a part of this, okay? Oh, thanks. Yeah, forgot all about the spin. Okay, we're back. Okay. Yeah, you didn't miss anything. It was just me talking. Okay, so here's the deal when you look at how this plays out mathematically. So there's a whole bunch of things that you can begin to set equal to each other. So work can equal the change in the kinetic energy. So for now, we're just going to deal with translational kinetic energy. So that can be written as kT minus kT naught, final kinetic energy minus initial kinetic energy. And you could write that as 1/2 m v squared minus 1/2 m v naught squared. Okay, and if you wanted to get fancy, you could write that as 1/2 m v squared minus v naught squared. Okay, so there's a whole bunch of different ways you can write that equation. It doesn't make any difference. Okay. So what you're going to have to keep track of, because there's so many things that you can set equal to each other, that what are you going to hold constant and what are you going to change? So, and all of that work still equals force times distance. So if I look at this, so I'm going to take this ball, Matt, and I'm going to throw this to you. Okay? So what's the initial kinetic energy of the ball? 0, right? So I'm going to exert a force over a distance, and I'm going to change that kinetic energy. So I'm going to do work. I'm going to change the kinetic energy. Oh, that was a horrible throw. Throw me that ball back. That was horrible. Let's act like that never happened. Okay. So I'm going to throw this to you. I'm going to do work, right? So now, did Matt do work when he caught the ball? Yes, Matt exerted a force over a distance because he decreased the kinetic energy of the ball. Now, the same thing is true. All right, Matt, give it a throw. Now, if I don't catch it, okay? If I don't catch the ball, guess what? I don't exert a force. Guess what? We don't change the kinetic energy. Okay? So just like you have to have a force acting over a period of time to change momentum, you have to have a force acting over a distance to change the kinetic energy. Okay? Same idea. All right. Earthquakes, right? It used to be in lectures about kinetic or potential energy, I would talk about earthquakes and the kids would never be able to understand that concept. Oh, we live in Kansas. We don't have earthquakes. If we live in California, okay, legitimate thing. But now, have you all felt any of the earthquakes? Okay? And it's unnerving. I remember the very first time we had an earthquake. It was a Saturday night. I was watching the K-State Oklahoma State football game. This was about 5-6 years ago. And like the bed shook, and it was like, oh my God, that is like the weirdest thing. And it was the first time I'd ever felt an earthquake. So if you look at what happens in an earthquake, it's just potential energy changing into kinetic energy. So at the fault lines, or some boundary, you store potential energy. And then something slips, and that potential energy, oddly enough, changes into kinetic energy, and you feel that as an earthquake. Okay? So all earthquakes are is a transformation of one type of energy into another type of energy. So even if you look at like a,
Nuclear explosion.
like a, huh? What'd you say?
It's a nuclear explosion.
Well, that's kind of, yeah, that's potential energy.
But if you look at a rubber band.
Yeah, or a rubber band.
Slingshot it.
So if I want to store energy in the rubber band, what do I have to do?
Pull that.
Pull. I have to do work, right? Okay, I have to pull this back. Then when I let go of it, that potential energy is going to change into kinetic energy. Okay, same idea. Now, what you want to focus on is that if you look at work equaling force times distance, go back to this, what we did with Kara, remember, and we had like the different weights cars, okay? And we had the string, and then one of them had like the weight on top of it, okay? So, if you look at the idea that work equals force times distance, if we have the same force, that weight hanging down on the end, and they act over the same distance, you're going to get the same change in the kinetic energy. Now, this one, the one that has more mass, because it has more mass, it's going to be going slower. But it's going to have the same kinetic energy as the one that has less mass, which is going to be moving faster. So that's why I said work is force times distance. Oh, that's your change in your kinetic energy. Force times time is change in momentum, which is just going to be mass times velocity. Okay. Got the idea? Got it? Good? Okay. So let's talk about the assignment.
Made a little pendulum. That broke.
The pendulum is still moving past first.
Oh yeah, we just got a long bar.
Huh?
Maybe it's one of the X version, but
No, but it's moving in an opposite direction.
Okay.
You're just doing it.
So when you look at like this question about
Coriolis.
on number 10, and this is where we're going to go old school even with Kepler's third law of motion. So when you look at Kepler's laws of motion, here's this elliptical orbit. So a quick refresher. When does a planet have its greatest velocity? It's closest. So guess what? Oh, that's when it's going to have a lot of kinetic energy. Now, because it's a distance from the sun, just like I lift up this block, I store potential energy. It gets further from the Earth. So basically what happens is you have this transformation. So when it's closer, you have a lot of kinetic energy, but you don't have as much potential energy. When you go out here, it's like stretching a rubber band. When you go out here, you're increasing the potential energy, but what are you trading off? You're trading off the kinetic energy. So then you're decreasing your kinetic energy. But all of that energy stays the same, and this is this whole idea that energy is being conserved. Okay, now when you get to question number 14, okay? On question number 14, you're going to get the same answer again and again and again. Now, I'm not saying you'll have the same answer all the time, but you will consistently get the same answer, because on 14a, you're going to find the work that's done. Oh, okay. Then that's going to equal the change in the kinetic energy. And then your change in the kinetic energy is going to be final kinetic energy minus the initial kinetic energy. Okay? So you're going to get the same answer again and again and again. So basically what's happening on number 14, if you were to look at like a kinetic energy versus time graph, the train's going to start with no kinetic energy. You're going to make it speed up, and then you're going to make it slow back down. So your kinetic energy is going to go from 0 up to a maximum, and then you're going to stop the train, and you're going to take that kinetic energy back down to 0. So your change in your kinetic energy is just from when you start at rest to make it speed up, is going to have the same value as when you slow it down. It's just going to have an opposite sign, because you're going from like 0 up to like 800 joules, and then you're going from 800 joules back down to 0. So don't be afraid to get the same answer again and again and again. So, anyway, so I'm good. So you're on your own.